Dr. James Sy and Ernée Robinson will be presenting on Georgia DOT's micromilling and thin overlay. Dr. James Sy is a professor in the School of Civil and Environmental Engineering at Georgia Tech. His research focuses on the application of 2D imaging, 3D lasers, 3D LiDAR, and GPS GIS technologies with artificial intelligence and pattern recognition to pavement asset health condition evaluation, preservation, and management. Dr. Sy has successfully developed and implemented the complex, large-scale, risk-based Georgia Pavement Management System, GPAMS, for Georgia Department of Transportation to assess, preserve, and manage its 18,000 centerline miles of highway. Dr. Sy is also a PI leading an interdisciplinary research team with faculty from CEE, ECE, GIS on a more than $3.5 million contract from competitively selected projects on remote sensing and GIS-enabled asset management, sponsored by the US DOT to intelligently detect roadway assets and assess their condition by using emerging sensor technologies. Now, his counterpart today, Ernée Robinson Perry, is Georgia's Assistant State Maintenance Engineer and has worked for the Georgia Department of Transportation since 1997. She has over 20 years of experience in transportation. She holds a Bachelor's of Civil Engineering from South Carolina State University. Mrs. Robinson Perry, her primary areas of expertise include construction management, project management, maintenance, and asset management. Ernée is the Vice Chair of the Southeast Pavement Preservation Partnership and the Vice Chair of the Roadway and Roadside Twig for AASHTO's Subcommittee on Maintenance. She is a liaison for AASHTO's National Transportation Product Evaluation Program and serves as Georgia's representative for the Southeast Regional Equipment Operators Safety Program. Additionally, Ernée is actively involved with numerous research projects with Georgia Tech, and she enjoys life with her husband of 14 years and their 2 children. She also enjoys music, reading, and coaching boys baseball. Please join me in welcoming Dr. James Sy and Ernée Robinson.
Okay, thank you. This one here aligned quite well, actually, tied with Adrian's first talk. So Adrian set a very good stage for us. In fact, I think she mentioned about the performance measure or end product. I think that's going to be our focus. So what we are going to, before I talk, actually, I would like to acknowledge that the sponsor, this project here is sponsored by Georgia DOT, as well as with some of the sensing technology. In the past, we putting together is sponsored by US DOT to do the performance measure. So this is the following. Ernée is going to first talk about the micromilling and introduce a little bit, and especially specific motivation why Georgia DOT wanted to do the micromilling and thin overlay here. And then I would kind of go through the rest, set up the objective, as well as introduce the procedure of micromilling and thin overlay. And the specific focus here is in terms of long-term benefit, because people wanted to know you save the money, but in the long-term benefit, what kind of performance that is going to be.
For a second, I almost thought I got out of this. Adrian did such a great job covering it. Okay, so basically, what is micromilling? Micromilling is an operation that you can use a much finer and smoother texture. The micromilling itself, it allows you to use smaller drums, which actually gives you a much smaller ridge to valley measurement. As you can see on the conventional side, you're using a much larger drum of 9 millimeters, and what we're using as for micromilling, we're using a 3 millimeter drum, which gives us a much smaller ridge to valley. Micromilling itself has several different advantages. You'll see that the improvement of the surface, smoothness, comfort, and also for safety. We had a project on I-95 that we did, and it's around our coastal area. And once we actually wrote the project and checked the IRI, it was actually lower than 825 millimeter, which we all know is kind of comparable to real new pavement. Another advantage to micromilling is to improve your work flexibility. It allows you to actually get traffic back on the surface a lot faster, and also allows the contractor to arrange his pavement operation. He has flexibility in arranging his pavement operation. Another advantage is improve the overall quality. It creates more of a uniform surface and a better bond to our overlay than it would in a normal conventional milling surface. It saves material and cost. It allows you to be able to use much thinner layers and even in more porous surface. Some of Georgia's motivations to actually go towards micromilling, because we're always constantly looking for better pavement preservation methods. And in 2007, we decided to go along with this research and to look into developing a new pavement process for micromilling, which was supposed to be showing us a better cost-effective replacement only on our thin open grade lift. Instead of actually going in and milling down the traditional 1.5 inches, we decided that we would only take off the very top layer of our OGFC because we identified that the bottom layers were sound. Some of our other states like Virginia and Maryland, they are also using micromilling, but most of it from we're looking at is for good ride surface, where in Georgia we're using it, but we're also using a thin overlay also. Basically, we'll take out a 7/8 to an inch of our OGFC and replace it back without disturbing the sound base. We found this to be a great cost savings. We identified from time to time on our I-95 project that we did, it saved us about $60,000 per lane mile. For just an example, we had 14 miles on that project, 6 lanes. There was a cost savings of more than $5 million. I think we kind of touched on this one a little bit, but just to kind of show you the actual detail itself, if you look at the conventional side, you'll notice that you have your 7/8 layer of OGFC and then 1.5 inches of the SAMA. That's normally what we would actually go through and mill out during conventional milling. But on the right-hand side, on the micromilling and thin overlay, you'll see the red box where we're just showing you a typical section of just the OGFC being removed. To ensure the success for this program, we've implemented new processes to ensure that we're actually meeting ride qualities. The construction procedures, we allow them to go in, they do pre-treatment, micromilling, they clean. We normally, before we start a job every night, we'll take a 1,000-foot section, we'll adjust the section, making sure that we are meeting the milling speed and the drum speed. We also verify that we actually have the ridge to valley depths that we're trying to achieve by going out, and we will use an automated RVD, which is a ridge to valley measuring device. We have modified our laser profilers to actually be able to retrofit them to be able to provide a faster continuous measuring. When we noticed that we're able to get more real-time data and real-time feedback when doing this. If anyone is interested in knowing more about our specifications, you can actually find it on Georgia Special Provision Section 432, Milling Asphalt Concrete on micromilling. Some of our typical projects that we've done, I-95 was one that we did in 2011, which was 100 lane miles. I-75 was 2007, 96 lane miles, and I-285 in 2008 was another 100 lane miles. We're currently working on the downtown connector now, the one that Adrian spoke of, and we've had some issues with dusting, and we've had some issues with allowing getting that water on. But some of the things that we're saying, like if we're allowing the cars to get on there earlier and let them ride and have the road for several days, we notice all of that dissipates and we get a much better bond. So we're kind of proud of what we're doing with micromilling in Georgia.
Okay, this one here, I think Nate just mentioned, so I kind of summarize a couple of things. Actually, in this one here, originally, as earlier Nate mentioned about that most of state DOT kind of using the micromilling just in a way that a smooth ride. But Georgia DOT say, well, the button there, 1.5 inch SMA, typically mill that out and replace that. they decided, say, well, if they can put in a smooth surface, the underneath is still, even serving 15 years or 12 years, is still good. You do not touch that. Just leave it there. The SMA continue on. So there's summarize in terms of a couple of new things there. One is a new design. So the concept there is in terms of you're just milling out OGFC 7/8 inch. You did not touch anything underneath. And then second is basically enhance the new micromilling operation to generate. So like using the drum and all of those. So from the contractor industry, they kind of bring this one in. So we kind of set up a spec first. In a way, is a reach to wallet, because on the OGFC, a lot of time is you, in our case, actually OGFC is on the top 7/8 inch on the interstate highway. You directly just putting that layer. So the surface, the water drainage, it becomes very, very crucial. Therefore, I think we set it up and putting together a new indicator, which is reach to wallet. That texture indicator to try to ensure the water can go out smoothly is smooth enough, and water not sitting there to laminate the surface, because otherwise it's going to be gone very quickly. So there's a new texture indicator that been putting together. Earlier, I think using the handheld test is really not practical. So later on, kind of retrofit and putting that together in the 3D laser, so you can real time, every time 0.5 mile. After the milling in 1 mile, you test 0.5 mile and get a result very quickly. In the end, there's a specific spec and come out with that one there. So I think one of the key research people would like to ask is related to, this one here is a save lot of material. We did not even quantify the cost, like Andrew mentioned about the green saving. This is just material cost. You can up to $5 million just in one project. Roughly like $60,000 per lane mile. But some of the people with a key questions say, well, compare with conventional milling, conventional method, what is the actual performance? I think people are like, you save a lot of money in here. I think if you look at the bottom there, because those are the different there, because you are going to mill out conventionally, you have SMA 1.5 inch. Now you decided, say, after serving 12 years, you're not going to mill this one here. You just put on the top 7/8 inch. And people ask question about, say, well, what's the life? Originally, I think it's about Georgia DOT quite conservative, say, well, roughly this is 5 or 7 years life. But I think right now is almost 8-9 years already. So we can actually see the performance, see how they perform. So this is the one I'm going to present it to you. So objective here is just quickly showing the procedure of micromilling and thin overlay. And then the second one there is a critical one, is to critically evaluate the long-term performance and long-term benefit in comparing between the micromilling and thin overlay and also the conventional one. So this is the procedure there, and just quickly mention that on the left-hand side there, that is the one that basically conventionally, that basically you mill out the whole thing there, 7/8 inch and 1.5. And now that certainly you can kind of mill the whole thing using SMA, but basically the whole operation right now we have is on the right-hand side. Basically, you do not touch the SMA. So that's the saving there, because you did not touch the one underneath. But keep in mind that need to be largely, because most of the underneath are larger sounds, so you can operate this way here. So now the first thing here is basically you need to set up 7/8 inch, because you only mill out the top OGFC layer on the interstate highway. So you need to set it up, and then you mill out 7/8 inch OGFC. And after that is milled out, there's a cleaning procedure putting there. And once this is finished, basically you kind of open to the traffic. In Georgia, I think we kind of leave that allowed to kind of 3 days. And part of the reason for that is we feel the traffic can clean out the dust itself and making that a better bond. And second is you provide a flexibility for the contractor coming back, which is after all the project been milled, then they can do the inlay in one time. So this is the one that keep in mind, quality control is quite important to make sure that there's no voids. So on the right-hand side, you can see that underneath here, the surface here, they expect to be smooth. and the surface with void there, those are the one that you do not expect to see, because all you see, those are uniform, open grade, and the water is more likely sitting in the interface layer. So you don't want a water sitting there that delaminate the surface layer. So this is the one that set up a new spec, and in terms of, so in the past, typically only one performance indicator, which is IRI. And so the operation there is that after you finish 1 mile, you immediately do the test, drive through, real time, print out the outcome, and see accept or not accept to move to the next mile. So at bottom there, you can see that the report there, it will report IRI as well as MPD, and then also reach to valley depth. In a minute, I will show that to you what's mean the reach valley depth. So this is the definition of reached valley depth. And basically, we measure the sample length as 100 millimeter, which is similar to the AASHTO standard for the MPD measurement, one sample size, which is 100 millimeter. So basically, in order, the simple way to see is a reach, the highest point and lowest point. The physical meaning is you wanted to make sure the water is not sitting there. So in that 100 millimeter here, you don't want it to a high upper point and the lower point. So that's the way that we set it up. So if you look at this one here, you can see that this is the travel lane there. On the left-hand side, that is a smooth surface. On the right-hand side, that's a little bit rougher surface there. So at the very beginning on line 95, I know that there's a couple of miles that just one lane. I think that has been redo because the reach to valley not meeting the requirement, because once finished, you'll do the test right away. And so in the quantitative analysis, you can see on the left-hand side, right side, if you look at the reach to valley distribution, basically you can see the smooth one there on the top is quite smooth. The reach to valley, in terms of millimeter unit, you can see that that's almost 2 or 3. So that's very, very smooth, very uniform. On the bottom, I mean, the bottom there is quite rough, which is referred to the previous one here. It's on the right-hand side. It's quite rough there. So you can see the distribution there. Mean is almost close to 4.5. In GDA, at this point in time, setting up 3.2. Average value, that's a requirement as a spec. So this is the one that we even capture some of the sample there, bring it back, because we wanted to know what's the quantitative texture there to do some of the study there. And this is the one that I want to share with you in terms of I-75, since it started in 2007. That is been set up. So we can see actually what's the performance now, because it saved a lot of money out front, but what's the life? So this one here is 15.3 miles, 6 lane. And this is the original design. Originally, this is a joint plain concrete pavement underneath, built in 1964. And as you can see, this on the left-hand side, those are the design. And AC overlay is conducted in 1994. And then micro milling and thin overlay is being carried out in 2007. So when this one here being carried out, you can see on the bottom image there that was the image, a picture taken at that point in time, 2007. That was the condition there is not quite good. So typically, the how long you expect to have in terms of life, roughly in the interstate highway, you expect that if you putting the typical pavement required resurfacing, like roughly 10 to 12 years. That is a typical timing for you to do the resurfacing. So now let's take a look in terms of the one that micro milling and thin overlay, and you just replace the OGFC basically with super thin layer. So in the 2015, actually after 8 years since 2007, you can see the rating is still 85. And typically in GDOT, they set up a timing for 70. 70 is the time they do resurfacing. That's earlier I mentioned it to you, conventional method, they expect basically lasted 10 to 12 years, and that was the timing, typically is time to do resurfacing. Originally in GDOT setting up for the micro milling thin overlay, they're afraid about, because this is a lot of unknown. They don't know what the performance is going to be. So in the report, they kind of put in 5 years or 7 years performance. But right now, as you can see, it's already 8 years. And 8 years still 85. So you still have several years to reach 70. So it's almost very similar life So, and we further look into the performance in terms of distresses, the Corpus system there. So you can see that this project here, once they're putting together in, so 2007 here, that is the 1 micrometer thin overlay. And you can see that the cracking started reported in 2011. And then 6 years later, that the raveling starving occurred in this case here. So basically, that's kind of performed quite well. And if you look at this one here is a 3D data. We kind of do the 3D data collection to take a look. So this is the one data collected in July 2014. So this is specific some of the problematic spot. You can see that there's some of the crack, specific reflect cracking, because underneath that's a concrete there underneath. So you can see this is the performance here. So for the new method there, basically it's not too much a problem to be able to achieve 10 years. If you say the conventional method, there's 10 to 12 years. Therefore, we kind of compare and do the life cycle cost analysis to get an idea in terms of 14 years and 12 years, what's the difference there. So there's in terms of saving there, that basically in the short term there, like in Georgia there, if there's a 1,300 centerline miles, 6 lane, if you apply this one here, basically the saving could be achieved like a $480 million in 10 years time frame, because if your life is 10 years. So there's a lot of potential benefits. So the one I presented to you basically is almost after 8 and 9 years, what's the actual performance. So far it seems like it's performing quite well. So GDOT kind of continue putting the spec and continue putting to different projects there. So this is the one that, and when we're moving forward there, this is the last 2 slides. So this one here has been kind of proved to be cost effective. And so the case study showing that the new method there has a service life and is going to be more than 10 years. So estimate costs in 10 years time frame, if in a Georgia interstate highway could save $480 million. This is just, again, this is just material cost, not counting the other benefits, sustainability. So other benefit there, including the reduced recycled material, environmental friendly or less traffic congestion, improve safety, etc., because you shorten the time in the whole process there. So those are the one could be further quantified. And this is the last slide here showing that it would make sense to incorporate this new method to GDOT's life cycle pavement preservation practice and management. Currently, Georgia DOT also tests and validate on interstate highway with OGFC with a FOX seal. So basically, at the very beginning, you may use a FOX seal to extend a few years. And then before you replace the entire SMA, you may be coming in just using a micrometer thin overlay. And after another 10, 12 years, and you're probably just using the micrometer, you can use a micrometer, and then you replace the SNA for 1.5 inch. So you can extract the life for a long time, at least 39 years in a longer time frame there. So that's the one that is kind of interesting to look at the whole life cycle perspective. The other one there is probably study the criteria for micrometer and thin overlay. Earlier when Georgia DOT is setting up, in selecting the project very rigid. Basically, you need to do the structural test, everything is sound, and then not too much of the distresses, especially the low cracking. But right now we're thinking about, say, well, is it structurally sound? You don't have to replace the SMA. If there's a cracking and the cracking there is a low severity label and even to certain level of severity label, would that be still valid to be a micrometer thin overlay? In short, I think in the past there's quite rigid criteria for the qualified project to do the micrometer thin overlay, and then maybe potentially can release a little bit. And the other one there is develop a pretreatment method. In the past, for those projects, the one I showed it to you, if there's a severity label 1 in Georgia DOT PACE's condition survey protocol, basically they do not do anything. Severity label 1 cracking, basically what they did is just the same thing there, putting the tackle. But in the future, would that be meaning for the pretreatment there, you can put in some of the even routing or even test different materials. So there's an ongoing project there, which is kind of continue every 100 foot and continue of distresses. And then you put in the one that we just the filling and with the filling different material. And then some of those with routing and routing with different material to see what's the performance. They have different costs associated with that. So that's related to pretreatment method there. Can further refine that. And as already I mentioned, quantify the environmental impact. And eventually, maybe could be a good alternative method, preservation method can be kind of shared with national, and so there's a need putting this national standard and spec. Yeah. With that, thank you very much. I think that's a good question. So the question was, maybe I repeat the question. The question was the reach to valid. Is that a piece of equipment or something or GDOT on or as a matter of fact, the reach to valid is a measurement. So the measurement itself the same as an MPD or the other measurement. So it can be computed. So as long as, so earlier I think we kind of compute that one there using some of the approach there. But later on we say, well, in order to make this approach here be able to have broader impact, a lot of people already have an IRI laser profile measurement for spec measurement. Why not? And that is data already there. So why not just use that data and retrofit, just adding one computation to compute and report RVD. So basically, in Georgia DOT's case, do not have any extra devices at all. Basically, just say, putting the computation in this software here, laser profile, every state DOT already have. And how about you just compute additional reach to valid depth? And then you come out the outcome to do the spec. That's a very good question. Yeah.
The thin overlay that you used, was it different or special than the thin overlay that GDOT normally used? The reason I ask is because my inner academic is wondering if you got good results because you micromilled first or because you used a better thin overlay than normal.
I believe that, well, the conventionally, as earlier I mentioned, conventional milling, that's what we're showing there. That I think Andrew's kind of also showed that the only two type. One is conventional milling. So the milling itself, you can see the reach to valid depth almost roughly in a quantitative term, 9 millimeter. So kind of highest point, lowest point. But the one, the micro milling there, that the one, as you can see, kind of roughly around 3 millimeter. So in a way, it provides a lot more smoother surface. That's kind of, I wanted to kind of summarize and kind of get back to Andrea mentioned. Yes, you have different machine there. Probably from GDOT or from our point of view, say, no matter what kind of machine you use, it's okay. But can you produce this product? And the product we kind of setting up at that point in time, say, how about we using the reach to valid, be able to quantify them. So in a way that right now, one of the contribution for this one here is come out as a quantitative procedure there that you can measure what would be the quantitative measure that you can achieve that. And but answer your question, in the past, Georgia DOT only one is conventional, so reach value roughly kind of, that's quite typical, 9 millimeter around their range. But the one that in micro milling, they're roughly kind of 3 millimeter. And then GDOT setting up a spec is 3.2 millimeter as a spec. Okay, thanks.
Right. Thank you very much. Can I have a hand for Dr. Tsai and Erne? And,